All right, let's work on this problem. Example 13.10. We are trying to find the local extrema of this function. All right, now the domain of this function is all real numbers, so there is no boundary, and the partial derivatives are going to be nice and smooth. So we only really need to look at points where our partial derivatives are zero, right? Because they're always going to exist. So let's find our partial derivatives. Fx, a function of x and y, will be minus 6x plus 6y. Our partial in y will be 6y minus 6y squared plus 6x. All right, so I'm looking for zeros of my partial derivatives. If I set my partial with respect to x equal to 0, that tells me pretty quickly that y has to be equal to x. I'll set my partial with respect to y equal to 0. And with a little bit of algebra, we find that 0 must be y minus y squared plus x, getting rid of those 6's. 0 is y minus y squared plus y, using the fact that I can replace that x with a y value in order to make my partial with respect to x 0. And then once I'm here, this is a quadratic that factors pretty nicely. Y is going to be 2 minus y, or sorry, 0 is 2 minus y times y, making y 0, or making y 2. So that is going to give us 2 points to look at. We need to look at 0, 0, and 2, 2. Okay, so these are local extrema, so they don't have to be bigger than everything else around it, or sorry, not everything else around it. It doesn't have to be bigger than every other point or smaller than every other point. So we don't want to just evaluate this function at these points and then see which one's bigger or smaller. We need to use our second derivative test to figure out the concavity of this function at those points. So in multiple dimensions, we look at the Hessian of a function, which is the second order homogeneous mixed partials. Sorry, that doesn't make any sense. The second order homogeneous partial derivatives minus the square of the mixed partial. And because these are continuous second derivatives, you can do mixed partial xy or yx, doesn't matter. All right, the second order homogeneous partial with respect to x returns a minus 6. The second order in the y is actually a function of y, 6 minus 12y. And you can take either x and then differentiate with y, or you can take the partial with y and then differentiate with x. Either way, you find that it gives you a 6, so you need to subtract off 36. Okay, so let's find the Hessian at our 2 points of interest. Let's look at 0, 0 first. So my Hessian, in fact, before I do that, let's just clean this up to make the algebra easier. We can simplify our Hessian as 72 minus, 72y minus 72. All right, now our Hessian evaluated at 0, 0, our first point of interest is going to give us a minus 72. So a negative Hessian means that the second order derivatives in xx and yy are different concavity types. Right, that's what gives us those saddle points. So at 0, 0, we don't have a minimum or a maximum. Okay, let's look at the Hessian at 2, 2. So plugging in y is equal to 2 into my Hessian, I get 72 times 2 minus 72 puts me at a positive 72. That's positive, meaning that the second derivatives share the same sign. I don't know if it's going to be a maximum or a minimum yet, but I can look at either second derivative, and at the y value of 2, my second derivatives are negative. So I have negative concavity, and the Hessian told me that it's negative in both directions. So this is going to give me a local max. Now, to figure out what the function value actually is there, what is the local maximum, just plug in 2, 2 into your function. Let's see, I think we get an 8. So saddle point at the origin and a local maximum at 2, 2, resulting in a maximum value of 8. Let's look at the picture. This is that function. And we see right there at point A, a local maximum resting over the point x is equal to 2, y is equal to 2. And at the origin, we see neither a local maximum or a minimum, right? That's a saddle point right there.